Hi, this is ET350 Lecture 8. Today we're going to talk about magnets, specifically permanent magnets, and we'll look at neodymium. That's actually these guys right here, neodymium magnets. We'll talk about magnetic field strength or intensity. It's the physical quantity is the magnetic field strength, and the unit is an amp turn per meter. Another common unit, well, maybe not so common, it depends on how you see it. It's Oersted, and it's the same thing, except it's just 1,000 over 4 pi amp turns per meter is the same as an Oersted. We'll look at how you create a magnet. We'll look at this thing called the BH curve and a hysteresis plot. We'll talk about magnetic attraction, and then the last thing we'll cover is core losses. And there are two types of core losses. One is hysteresis and one is eddy currents. Okay, and we'll look at an example. So let's look at permanent magnets and what's a big pro of having a permanent magnet, for example, in your motor or generator. Well, one is compact, and you don't need any extra field windings and source or an extra source to power it up, right? The magnetic field is inherently created in the material itself, so kind of cool. Well, what are the cons? Well, you're limited in the available flux density, right? You can't just turn up the current and get more flux density. So you're just stuck with what you get. Whatever this is, that's it. The other problem is you can demagnetize it. If you're heated past this TC, or what we call the Curie temperature, it'll lose its magnetism. All the domains, we'll talk about the domains, and they will go in random directions, and that's not good. You can drop a magnet or you can hit a magnet, and impact will make these domains kind of scatter all in different places. That can demagnetize it. Well, also, this is kind of a weird one, but you can expose, if you expose a magnet to a decaying oscillatory current or field, that can actually demag a magnet. And that's interesting. So what does that mean? So if you had a current creating an electromagnet, an external electromagnet, and you saw this kind of decaying kind of signal, and it exposed this magnet to this decaying magnetic field, you could kill a magnet that way. And it's kind of interesting to see why. And when we look at the BH curve, hopefully we can understand why. Some interesting things about ferrite magnets is that they can demagnetize with cold temperatures. So if you're shipping magnets, you got to make sure that the temperature is maintained in the operating range. However, ferrite magnets specifically have great high temperature characteristics. They're not like neodymium where they demagnetize as readily. Okay. All right, so the strongest commercially available are these neodymium. So they're made of neodymium, iron, and boron. It's a rare earth magnet. Truth be told, they're not that rare, however, because there's a lot in the Earth's crust, but China has a lot, probably due to maybe less regulation. They're found in hard disk drives, so if you want to get some free neodymiums, just rip apart a hard disk drive. However, they have a low Curie temperature, so only 80 to 320 C, depending on the manufacturer, which is equivalent to 176 to 608 Fahrenheit. The other thing is they can corrode, so that's why you have this silver shiny coating on it. But they do have a high HC, and what HC is called the coercivity. Okay, it's related to this magnetic field strength. And they also have a high remnants. Okay, so this is gonna, I mean, these numbers kind of don't make any intuitive sense yet. This is about 0.875 to about 2 mega amps per meter. And then the remnants is about 1 to 1.4 Teslas. So that actually, if you're something in the 1 Tesla range, that's actually a pretty strong magnet. Okay. All right. So let's talk about this H, right? We know what B is. B is units of Tesla, it's magnetic flux density, but H is kind of a new thing. It's called the magnetic field strength or intensity. It's the symbol H, and it's the unit of amp turns per meter. So really H is essentially from current. More current, like current in a coil, creating a magnetic field, more H, okay? Some units are also Oersted. Like I said before, 1 Oersted is 1,000 over 4 pi amp turns per meter. And like I said, the magnetic field intensities depend on the current and coil configuration, and it'll be shown that B depends on this H, okay? So when you see H, I want you actually to think of I, current, right, instead of just H, because I think that'll be less confusing. So for example, if we looked at our Ampere's law for a inductor or a coil, we can use our right-hand rule, we can see the direction, but this is the equation that gives us the quantity of B with respect to I, right? This was B equals mu Ni over L. We proved this in a previous lecture, and this is Ampere's law. And notice amp turns per meter. This is H, in fact, right? And H is related to B by this permeability of this core. So you can see more I, more B, more H, if this is H, more B. And so here's another way to write it, B equals mu H. And if we were to draw a plot of this BH curve, we would see something like this. H equals Ni over L as I get more H, which is essentially caused by more current and some of the configuration, I get more B. Okay, so is that true? This is not always true, okay? And here's the reason why. It all depends on the configuration of the magnetic domains going on inside this material. So this is not going to be this nice line, right? You could think of this nice line as if there was, no funny nonlinear business inside here, right? It's just a simple, yeah, more B, more I, okay. But in reality, it's something different. So imagine you start with a ferrous core and we put it inside this coil just like you have here. This is the start of a raw magnet. This is like the raw material. It's not a magnet yet, it's ferrous. And so what you start out with is you have essentially a lot of little magnetic domains. They're all in random directions, right? And if you remember from chemistry class, you have your atoms and they have the spin behavior and they have a dipole in this moment. That's creating a magnetic field like behavior, right? That magnetic dipole, right? Just a little on the atomic scale. And then in ferrous material, you get a bunch of them clumped together. They're all kind of pointing the same direction for this island. And maybe this island's pointing another direction. This island's pointing another direction. So they're all pointing in random directions. So it's not a magnet yet, but it could be one. Okay, so let's say it's sitting here. There's no current. Remember, the current is related to H. Okay, so we're here at 0. And what happens is, let's say we increase H, which is increased by current. What you're going to do is, instead of going on a nice linear line, you're going to curve up to here until the point where you just saturate, and now you just go on a linear line again, right? You're getting no more nonlinear stuff. You kind of saturate. At that point, all the domains inside, because you have this external magnetic field pushing up, are now aligned with that external magnetic field caused by this H or this I, okay? Now, what would happen if I were to reduce this current back down to 0? Well, if the current goes to 0, the H goes to 0, and we go back to here. We don't go back to 0 like you would in this case. You actually go back to here. This BR is called the remnants, okay? So if I take away the current, I now have a permanent magnet, right? I've jacked it all the way up. I've got all the domains aligned. And when I release the current, I go to here. And now this is my permanent magnet. I have the coils pointed up, or sorry, the domains pointed up, but maybe a few relax back to their original random direction. But a lot of them are pointed in the same direction as that magnetic field strength or that current, that magnetic field from the current. And that's your permanent magnet. That's it. That's how you create one. So these coils are usually huge. They're thick so that you get a lot of current running through it. So you get a lot of magnetic field. So you can really snap those domains in the direction you want. Okay. Now, what happens if you start applying negative current, which would result in negative H? Well, you could apply enough negative current to get negative H to get to this point, HC. This is the coercivity. This is where the combination of the permanent magnet that you created and the external intensity cancel out to 0. Okay, you haven't demagnetized. If you pulled it out, you haven't necessarily demagnetized your magnet, right? It might bounce back to here. However, if you keep going to this point, HCI, the intrinsic coercivity, that will kill your magnet. Okay. If you keep going further, keep going more negative, you would actually magnetize it in the opposite direction. So what was the north on this side now becomes the north on the other side. Now, if I release the current back to 0, this would be like the remnants on the other side. you could keep going and then bring it back and remagnetize it again. This side would be the same as this side. You know, you bring it to 0, you could kill that permanent magnet, and then you bring it here. So you can see this, what we call a hysteresis curve, okay? And so this is your core, where you can turn into a permanent magnet oriented one way, turn into a permanent magnet oriented the other way, okay? And these are just the terms, coercivity and intrinsic coercivity. This is to bring both the permanent magnet and the external, they cancel together to get 0, but here's where you kill it. Notice it brings it even lower. Another way to think about it is to combine these two plots. So think of this as the normal curve, we'll call this a normal curve, and it's the ferrous material with the B mu H from the current. Okay, if that makes sense. So if I didn't have any like domains and all that stuff, and I was just able to operate on the permeability here, I would have this. So this has both. It has the domains and all that stuff and this, whereas this is just by itself. Well, we could subtract this curve from this curve and get the curve of the actual magnet itself. And that's what I have drawn here. So again, we have our magnet here, or ferrous material, we have the current, and this curve here is this one, this curve here is the previous one, and if I subtract this one from this one, I get this thicker line. Do you see that? This thicker line. It doesn't slope up like the normal curve. Now, what is this called? This is called the intrinsic curve of the magnet. You still have HCI, but now notice you have this new 0 point on your new curve. That's HCI. So that's the same as that HCI here. But now you can actually see why it's there, where it's coming from. If you apply enough HCI, you've killed the magnet, right? So that's the point. So we'll see this on a data sheet later in this lecture, but I just wanted to bring up what this intrinsic curve is. It's the normal curve minus the external curve from the H, right? And you can see that here. If you take this minus this, you're still at, you know, 0. This minus 0 is still this, right? However, this minus this, you get this flat line, right? Notice how this kind of cancels with this to make a flat line, right? Okay. You can see that at this 0 point, you're just left with this one, right? So hopefully that kind of makes sense. Okay, let's keep going. Another curve that I just want to show you is the comparison between a hard or a soft magnet. Okay, a hard magnet will have a bigger hysteresis curve, more area here, whereas a soft magnet has a smaller hysteresis curve. And I hope you can see that this harder magnet is going to have a bigger HCI. It's going to be more difficult to demagnetize that hard magnet. Okay. Okay. Now you've heard grades like N42, N38, N52. The higher the grade, the more force, the more flux density you can get from that magnet. Okay. And you might ask the question, where does that number come from? And this number is again related to this BH curve. And what it is if you have a BH curve for your magnet, it is the largest rectangle that you can make, and it's the area of that. Okay, and so maybe another question you might have is, well, what are the units? What are the physical units of that area? Well, if I take B times H, what do I get? I get Tesla times amp turns per meter, which is just amps. The turns is just like the number of turns of that coil. And a Tesla, what do we have? Weber per meter squared, right? Flux per area, yep. A Weber is a volt second, okay? And so we have a meter cubed on the bottom. So you have a volt second amp per meter cubed, okay? I can switch those, volt amp second. Well, what's a volt amp? We know what a volt amp is. That's power, right? So that's a joule per second. A volt amp is a joule per second. Notice the seconds cancel, so we have a joule per meter cubed. What's a joule? A joule is a Newton meter. So we have a Newton meter per meter cubed, so a Newton per meter second. So that means the area of this guy here is equivalent to either energy per volume or force per area. It's the same thing, energy per volume or force per area. Okay, so if you are traversing this, we're going to talk about this later. If you're traversing the cube, you're looking at energy burn, right? It's taking energy to flip these dipoles back and forth, right? But what you're also seeing is if I have a magnet that has a big hysteresis loop, I will also be able to produce more force, right? It has the capability of producing more force. Okay, so now let's look even closer at this. So for an N52 magnet, here's an example curve, right? And the biggest box I can get might have like the numbers 9.6 and 5.4. Okay, now the units are weird. It's going to be kilogauss. Remember, Gauss is the same as a Tesla, except there's a factor of 10,000, right? And there's kilo-Oersted. Remember, Oersted was also a unit of magnetic strength intensity. So the kilogauss times the kilo-Oersted, that number in mega Gauss-Oersted is going to be approximately 52 for this case. And this, if you saw this curve, this magnet, this would be a grade N52 magnet, all right? So that's how they get that number. They use kilogauss, kilo-Oersted, and look at the BH curve and the largest rectangle you can make with the BH curve. Okay, so let's look at a data sheet of an N42 magnet. Okay, so an N42 magnet, here's an example, right? N42, your residual flux density, they're going to quote you at 13 kilogauss. Your coercive force, or the HC, greater than 11 kilo-Oersted. And notice the HCI is bigger than this. It's greater than 12 kilo-Oersted, okay? And you can't just multiply these two numbers to get this. You got to go to the plot and look at this area. So let's go look at the plot. So here's a picture of a N42 grade curve. Now remember what I said before. You had your normal hysteresis curve and you had your intrinsic curve, right? These are your intrinsic curves. Okay, and I'll bring that figure back up. So the normal curve here, let me bring this up. Okay, you have your normal curve here. That is this one. That is this one here. And you have your intrinsic curve. Notice the intrinsic curve is a little bit higher, right? Okay, so let's look at this one specifically because that's the one where we're operating at, let's say 40 degrees Celsius, right? Okay, sorry, 20 degrees Celsius. Yeah, room temperature. So it's this curve here, this intrinsic curve here, and this normal curve here. Okay. Notice the HC, yep, greater than 11, HCI greater than 12, yep, meets all that. And if I look at a box where I can draw the biggest rectangle, you can see it's about 7 kilo-Oersted and about 6 kilogauss. 6 times 7, that's 42. This curve at room temperature of 20 degrees C is giving us an N42 magnet because 6 times 7 is 42. Okay, so just a convention of how they rate these magnets, right? Bigger area, a higher grade. Okay, I hope that I know there's a lot of information. I hope that starts to make sense. Okay, let's keep looking at these magnets. So you guys will be dealing with these when you build your motors, but it's good to have just at the tip of the iceberg some understanding of what's going on with these things, right? Okay, so let's look at magnetic attraction, right? So let's say we have some random ferrous material with random domains, just a piece of steel, and we take our permanent magnet and we put it in between. Well, what's going to happen to the top piece of steel and the bottom? Well, the domains internally will get aligned because of the external magnetic field introduced by this permanent magnet. And so what happens when you have magnetic fields aligned? Well, you get this attraction, bink, bing, and then these want to attract. You have essentially created a south pole here, and you've created a north pole here, okay? And so notice this has created kind of a north-south and a north-south. If I brought this piece of steel over here, it would still attract. It would align the domains like this. If I swapped them, they would still attract. So attraction occurs on either the north or south pole. Okay, because this, you can think of these materials as kind of flexible in their ability to change their north and south, right? Once you've made this like a permanent magnet, then now it's different. Once it has its own permanent magnet, it's kind of has its fixed dipole, then what happens? Then you guys already know, north and north repel, south and south repel, right? Okay, So what that a consequence of that is that an electromagnet can attract ferrous material even with AC electricity, right? So if you have an electromagnet with AC going back and forth, it'll still attract steel, just ferrous material. And I believe you guys have contactors that have AC electromagnets attracting steel. And so hopefully that answers that question. Well, why doesn't it repel? Well, because it's flipping the domains in the steel to maintain that attraction, right? So if this was an electromagnet flipping its domains back and forth, well, internally inside this ferrous material, they would get their domains flipped back and forth and it would still attract. Kind of cool. Okay, what I did was this morning I was playing with these BX044s. Okay, they're a 1 inch by quarter. They're magnetized this way, like you see here in this picture here. Okay, kind of this way, not through the axis. All right. And what I want you to kind of get from this little experiment that I did this morning is a feel for the magnetic field around these neodymium magnets, or just any magnet in general. And really the take home point is the magnetic field falls off very quickly with distance. So if you have your coils, your armature coils, right, your permanent magnets, let's say, are in the stator, and you have your armature coil spinning next to it, well, what's going to happen is that if you get your armature coils too far away, you're not immersing it in any magnetic field, and vice versa. Let's say you have a brushless DC motor where the magnets are spinning and the coils are stationary. It's the same thing. If your magnets are spinning, you're not going to induce any current if it's a generator situation, and vice versa. If your current is here, it's going to be more difficult to lock on and maintain that force. So you want to get your magnets as close to your coils as possible without rubbing and all that stuff. I know it's hard to see on this. I'll print a better copy in the posted notes. But if you look here, you can see how quickly we fall off to almost nothing. Like within, I mean, I know the colors are bad, but within one length, and I already did an experiment, so I'll show the results. Within one length, you're already getting into this light green here, right? And then within two lengths, you're like kind of near this blue, right? Nearly nothing. So it falls off very quickly. The other thing I want you to note is it's not uniform. Look how, yes, sure, right above, it's kind of perpendicular to the surface, but it starts bleeding to the left and to the right very quickly. So these are things you want to account for in your design of your structure, right? You want to think, well, if I have coils way over here or way over here, it's not going to do anything, right? First of all, the alignment is weird and the intensity is low. So this is like just all sorts of bad news over here, right? You want to be operating, you want to get your coils in this area as close as possible, okay? All right, so let's look at some experiments I did this morning. What I did is I measured the flux density. So check this out. I have, put this to the side, I have what we call a flux density meter. Okay, this is a Gauss meter, and it's hard to see. There you go. You can see the number here. Okay, and I can put it. Let me put it in the light. There we go. Perfect. I can put it on this magnet, and I can see the intensity, right, as I change the orientation. And so, on the surface of this magnet, we're getting about 4,000 Gauss, which is 40% of a Tesla, right? 0.4 Teslas. Remember, 10,000 Gauss to 1 Tesla, right? I have it on DC here. Okay. You can see if I flip the probe over, I get a negative number. Okay, good. So that's the surface of the magnet, right? So this is, let's say, 0 right here. And what I did was I measured essentially every 1/8 of an inch. So this is a 1/4 inch. So every half distance away. Can you see how quickly that flux density falls off? Wow. So so this is a 1/4 inch, right? So here's at the surface, here's a 1/4 inch, 0.25. I'm here. I went from 4,000 to 1,000. Less than 1,000, in fact, right? I went from 4,000 to less than 1,000, just one magnet length away, right? And you can see that number here, okay? If I go 2 magnet lengths away, here at 1/2 inch, I'm down to 300 Gauss, right? So very, very drastic fall off. And so I hope this hits home why you want to get your coils as close to the magnet as possible. Okay. The other little experiment I did this morning was to look at, well, what happens if you stack magnets? So let's say you go, well, if I take, a magnet, I put another magnet, will I get a stronger flux density? And yes, you will, but I wanted to plot, well, how much stronger, right? So I just stacked I stacked up to 10. And you can see you don't double. It's not like I get 8,000. Look here. I have one magnet and I'm measuring what, about 4,000. I put a second magnet, I just stack it and measure, and this is the peak. This is peak flux density at the surface. I didn't, do this fall off again. I just measured, just rubbed it on the peak. And I only get just under 5,000. And you can see as I add more magnets, I kind of like after 3 magnets stacked here, it's like diminishing returns here. Yeah, maybe a little blood, but this is all like noise over here. So stacking magnets helps, but it's like, well, anything after like the length of this, it's not much, right? So this is just something to be aware of when you are designing or picking your magnets. You guys are going to get a bunch of magnets, and so you can see how the configuration could help or hurt you, right? Be efficient with what you have. Okay. Let's keep going. Oh, by the way, I just wanted to show you some things that are nice. So this is a little magnetic, $5 on Amazon, a little magnetic pole tester. If you have a compass, you can figure it out, but here's red and blue, north and south. So the red is attracted to the south, obviously. So this, you can see it. You see how it moves? This is my south pole right here. If I flip it, look at that. You see that? Ooh, nice. This is my north pole on this side, right? If I move this around, can you see how, oh, careful, get that stuck. You can see it because it's on that gimbal. You can actually visualize the magnetic field lines, right? So you can see them swirling around, right? That's kind of neat, right? So this is kind of fun. You can see the magnetic field line. This is a magnetic viewing tape or a film. And so you can see right here, do you see that separation, that line? That's actually the differentiation between the north and south pole, right? You can see it's right in the middle because it's magnetized in this orientation that way. Okay, if I go and rotate it 90 degrees, see how I don't see any of that separation, right? Okay, but if I rotate it again, I can see that half. That's the halfway point between north and south. It's kind of neat, okay? Can I do the same thing for this? Yeah, let's see here. See, I see that line in the middle. It's not the greatest. There you go. You kind of see that separation in the middle, right? Kind of neat, okay? The other thing I wanted to show you was this. So here's an aluminum plate, not magnetic. And we're going to talk about losses in the core pretty soon here, not magnetic, right? So it doesn't stick to the aluminum. But if I were to rub this back and forth, and the faster I rub this back and forth, I can feel a physical resistance, like it's a dampy motion. And you can see it, like, see how it like slowly, slides down. It even tumbles because the forces, remember the Faraday's law is in action, Faraday's law and Lenz's law. What's happening is we are inducing currents in this aluminum that resists the change. So what's the change? The change is coming from gravity. Gravity is pulling this down, right? So gravity is creating a d phi dt relative to this conductor. In this conductor, it's creating swirling currents, we call eddy currents, and it's creating eddy currents in such a way that it creates a magnetic field that opposes that change. So that's why there's a kind of a resistance to it slowing down, right? Interesting. Whereas if I just put it on like a piece of plastic here, boom, it just slides down, no tumbling, no rolling, right? I need to get a pipe. I mean, all this stuff is in my classroom. But what's cool about this pipe, if you have you can drop it and instead of just dropping so quickly, I mean, you just Google it, there's YouTube videos on it, it'll slowly fall down, which is really neat, okay? And so once you get your magnets, if you get a piece of aluminum, you guys can play the same thing. You'll feel that resistance, and the faster you go, it's like, wow, that's really strong, okay? So this is all related to the core. And if you think about it, if you're inducing currents in here, you're inducing I squared R losses in here, you're inducing heat in here, right? So this, technically, this is getting warmer as I do this, okay? All right, so let me turn these off. Okay, turn this off, move this. Be careful with these. If you get multiple of these, especially the big ones, ooh, pinch, ouch, not good, blood blisters, all sorts. I got bit once, right? What a good way to store this is you wrap it up, put it in a pad, in a box, okay? So that way you don't get pinched. Another thing you could do is if you have a piece of steel, you could stick it to a piece of steel, because what'll happen is for steel, the magnetic field likes to be in the steel, something with high permeability. And it now will get sucked to the plate. Like let's say it's a whiteboard with metal, it'll get sucked to the plate. So now it has less chance of it jumping away. But if you have this just thing sitting in here and you get another magnet that's close, it'll literally jump out, right? And it can smash your fingers if you have a big magnet here, another magnet here, bang, okay? Super dangerous, right? Or worse, you could demagnetize your phone, because I'm sure some of you would be more sad to have your phone magnetized and destroyed than your fingers, because your fingers can heal, right? Just kidding. So store them in a safe place. I'm gonna put the right here on my lamp over here. It's just gonna sit there safely without, can't jump out. So don't get it close to your credit cards, your cell phone, your computers. It'll mess it up. So don't do that. Okay, let's keep going on this lecture. So let's look at losses in the core. And when I talked about the core, one example would be like a transformer. And there's going to be hysteresis losses, that's from the BH curve. And there's eddy current losses, the eddy currents that I just talked about, right? So let's look at the hysteresis losses. And we went through this, right? If you traverse this curve, you are having to flip those domains back and forth, right? And the bigger this curve is, the more area there is, the more energy per volume, right? And remember, we already showed that before. The BH curve, that area is energy per volume. And how do you traverse this curve? Well, here's your core. Think of this as a solenoid or one leg of a transformer. This current, let's say, is AC. So if this current goes back and forth, this H goes back and forth. If this H goes back and forth, this B goes around this loop. And every time you traverse this area, you're burning off this amount of energy per volume, energy per volume, energy per volume, okay? So I hope you kind of get a sense of why, right? It takes energy to flip those domains back and forth. Every time you flip it back and forth, this is getting hot, okay? All right, so for an AC case, the H will cycle the same rate as the electrical frequency. Right, that makes sense. If this is 60 hertz, this cycles at 60 hertz, no problem. And every cycle we have lost energy and a volume because of the area inside the loop, no problem. And it's dissipated heat. That means the power loss due to hysteresis is directly proportional to frequency. Okay, so this is alpha, my little symbol for proportional to. So what can you do for transformers? What could you do? You could minimize that loss by choosing a material with a thin hysteresis loop. Right? So you want something like this. Interesting. So that's kind of contrary to a permanent magnet. In a permanent magnet, you want something with a large hysteresis loop so that you can maintain that residual magnetism. But why do you want a BH curve at all? You want the permeability. That's the slope of this line. If this were collapsed to a line, you want the permeability so that you can get a lot of magnetic field transfer in the coil, but you don't want this turning into a permanent magnet. You don't want to have to be flipping domains, right? So some materials that are nice are, one example is grain-oriented silicon steel. A lot of the transformers are made with this. They have less area, therefore less hysteresis losses. Okay, so this is where the material matters. That'll help minimize hysteresis loss. Now, what about the eddy current losses? Well, that's where, we did this thing, right? So imagine you expose this plate, right? And it could be steel, it could be aluminum, any conductive plate, right? And you have current going, let's say, sorry, not current. You have flux density, let's say changing, right? Perpendicular. And let's say we have a phi that's increasing, right? Well, remember, by Faraday's law, we're going to have a phi opposed that fights that change, right? And we have by Ampere's law, we're going to have an I induced that supports that phi opposed to fight that change, okay? And so you can imagine the current's going to swirl in this clockwise direction if you have a phi going this way. Obviously, it'll flip if the phi increases in the other direction, right? So you're getting these swirling currents. So what can you do for a transformer? Well, to reduce these eddy currents, you chop it up and you insulate these sections, right? And you've seen these laminated sections before. And so what happens when if the flux density is wanting to increase and decrease in this axis, if you chop it up like this, can you imagine how the currents are now forced to go through this kind of hindered path, right? And so that's how they chop down the eddy currents, right? By just using these laminated sheets. So what they do is they try to insulate each sheet relative to each other, so current literally can't flow. Another way they can do it is like, imagine a powdered iron insulated binder, like you have like epoxy and then powdered iron. So you have these little bits of epoxy, right? But then it's in the slurry, or sorry, little bits of iron in the slurry of epoxy, right? So that the little iron has the high permeability you want, but they're not in direct contact with the other iron bits, right? Okay, they all have challenges, right? So maybe it has great eddy current dissipation effects, right? But maybe it's not as solid as this iron, and so it doesn't have as high permeability, right? So there are trade-offs. Okay, let's keep going. Now, let's look inside. Here's an example of a transformer core. Look at this. Here's your iron sheets, right? By Ampere's law, current's going to go up and down. And notice that's kind of like this, where if like I had the current going up and down, but look how the laminations are. They're this way, right? Same with this one. They're this way. And here's a picture of a real one. It's really hard to see with the light, but the laminations are running that way. You can kind of see it, right? If this is the coil wrapped around. Okay, so those laminations are to reduce the eddy currents. Okay, all right. Now, how do eddy currents relate to frequency? Well, remember, these eddy currents are burning off I squared R losses. Well, that square means that your eddy current losses are proportional to the frequency squared, not just frequency. That's a big deal. That means if you double the frequency, you're quadrupling the eddy current losses. That's a big deal, okay? Does this also happen for armatures that are spinning? Yes, it's the same kind of idea, because when you have like an armature that spins around, you are passing this steel next to an external magnetic field at a certain rate, at omega m, right? And so the power loss is proportional to frequency squared, or the angular velocity squared, right? And this eddy current loss in your armature. And so here's a way to think about it. Imagine you had a solid chunk of steel. You have flux density going left to right and it's spinning. Now remember, when we analyze the generator, you have some force opposed that's fighting this speed, right? That's what's creating your back EMF and all that. You have this current that's supporting this force opposed, right? So the force opposed is from Lenz's law. The I induced is from the Lorentz force. It's supporting that force opposed. And so what's happening is you're having this I induced at any given point that's wanting to circulate like so. Well, what could you do to stop it? What you could do is you could again chop it up with laminations in this direction to force these currents to have to take this narrow path, okay? Again, you could use the grain-oriented silicon steel and all that to get the high permeability, so that the B field wants to go into the rotor and then out to the next side, so you get the high permeability. But you have these laminations so that you reduce the eddy current losses, and then you choose the grain-oriented silicon steel to reduce the hysteresis losses. Okay. All right. Let's look at the next picture. So this next picture here is an example of a rotor. Notice this is the axis of its spinning, just like so, and look at the direction of the laminations. They're chopped up like this, so that when these currents want to flow like that, they can't, right? We want the current to flow in the copper wires. We don't want the current to flow in the steel. And that's a big reason why you see steel and copper. It's like, wait, isn't everything conductive? They're conductive for different reasons. You want the steel to be magnetically conductive, not electrically conductive, right? And whereas we want the copper to be just electrically conductive. Okay, good. So the last example is just a simple numerical example, and just to kind of highlight this stuff. So let's say you have a core, you have AC current going back and forth, so the flux density is going up and down. And let's say this is operating at 60 hertz, and they say the hysteresis losses is 1 watt and half a watt for the eddy current losses. Question is, what is the hysteresis eddy current at 400 hertz? Well, we know they're going to be bigger, right? We're increasing the frequency. Remember, this one is proportional to the frequency squared, and this one is proportional to just the frequency, right? And so I could write these down. Another way to write that is the hysteresis losses is equal to some constant times the frequency, whereas the eddy current losses is equal to some constant times the frequency squared. Same idea as this one, right? Okay, so well, what we can do is, well, we know this constant is equal to just P over F for the 60, but it's also equal to P over F for the 400. Well, I don't know what the P is for the 400. That's what we're looking for. But I know this is 400, this is 60, and this is 1. I could easily solve that. One equation, one unknown. I get 6.66. Okay, yeah, great, bigger. Okay, let's do the eddy current losses once. It actually starts out as lower heat loss. We could play the same game except for the E, right? Except it's P eddy current losses over frequency of the 60 squared. Notice the square. And P eddy current losses at 400 hertz over the frequency at 400 squared. So it's 60, 60, 400, 400, but squared. Here's what we can do. Same game. 400 squared, 0.5, 60 squared. Solve that ratio, and I get 22.2 watts. A whole lot more. Look, this was at half a watt, so less half of this. Yet look at this, 22 watts here. So this is really dependent on the frequency, right? This eddy current loss, okay? So I hope this example drives home some of the eddy current losses. I hope you learned something in this lecture, and yeah, I'll see you in class.